So now that you've learned a little bit about Java concurrency, concurrency concepts, concurrency features, especially threads, and a teeny-weeny bit about interacting through shared objects and through message passing, let's talk briefly about some of the concurrency hazards that can arise when you program with these types of abstractions. So these are some of the things that'll bite you if you're not careful when you're programming at this style using these features in Java. And we're also not only going to talk about some of the hazards that are addressed by using these mechanisms, we're also going to talk about some hazards that stem from using synchronizers themselves. So it's kind of like, self-inflicted wounds, as it were. So the two of the key things we're going to talk about here briefly that will be addressed by using either shared objects or message passing are race conditions and or memory inconsistencies, which are related to each other. They're often occur in the same context because people forget to put synchronizers in their code or they forget to pass messages properly, but they're also a little bit different. So what is a race condition? A race condition is a problem, very subtle and pernicious problem, that can occur when a program depends on the sequence or the timing of threads in order for it to operate properly. And again, I like to use the example of things smashing into each other, and that's exactly what happens. Typically what happens, there's a bunch of variations here, but what often happens is that one thread is reading and one thread is writing at the same time to a piece of memory, and if it's not protected by a synchronizer, you'll have race conditions, and whoever gets there first or whoever gets there last is the one who has the final say, and that's often not what you want. So let's take a look at a simple example. This is something called Buggy Queue. And you can go look at this program here. If you want to see how to make your program be buggy, you can take a look. But I will just give you a quick synopsis of this. So the Buggy Queue, as you can see here, has race conditions between producer and consumer threads that are trying to coordinate their interactions through an unsynchronized bounded queue. The keyword is unsynchronized. That's bad in this case. So here's what happens, chaos and insanity. So we make ourselves a list. In this case, it's an array list, but it could be a linked list for all we care. But this list is not synchronized by default. So a Java array list, a Java linked list is not synchronized. So if the offer and poll methods are called concurrently, in other words, thread A, thread B, or thread 1, thread 2, if they both call these things at the same time, then we're going to have problems because we're going to be adding and or removing from that array list without benefit of protection from a synchronizer. And so you'll end up with race conditions. So very strange and bizarre things are going to happen. If you want to learn more about this, there's this interesting article that is entitled something like, "Why Shared Mutable State is the Root of All Evil in Concurrent Programs." And that indeed it is. It's the root of all evil. So I usually use the scream to indicate chaos and insanity. To go from the scream to the happy face, I'm sure that Edvard Munch would be very disturbed by my modification to his wonderful painting. All we need to do in this particular case is just make these methods synchronized. So these methods are not synchronized, these methods are synchronized, and boom, problem goes away. Now there's other things more subtle about this, but we won't talk about them right now. So if you use Java mutual exclusion mechanisms, you can make these problems go away. This is an example of synchronized methods. There's also synchronized statements. You could also use reentrant locks. You could use stamped locks. I'll leave that to another class to explain why you would make one choice versus another. Another problem you can run into are so-called memory inconsistencies. And these can occur when different threads have inconsistent views of what ought to be or what should be the same data. So again, think transporter beam in Star Trek, think disapparating and splinching in Harry Potter and so on. So here's an example to illustrate. This is called loop may never end. And what we have here is we've got an unsynchronized and mutable shared data. Remember that in Java, Boolean fields are initialized to false by default. So this starts out at false, which is fine, but it's not synchronized. So what's going to happen here is chaos and insanity, because if we have thread T2 calling this method and thread T1 calling this method, then this method is sitting here basically saying while done is false, do something. And down here, this thread thinks it's going to be stopping this other thread because it's going to say, hey, done, you're true, M done, you're done, M done is done. But the problem is because this is unsynchronized, it may take a while, perhaps forever, for the change from this thread and its multi-core cache to be propagated over to this thread in its multi-core cache. And that's because this is not synchronized. The solution here is quite trivial. If we make this volatile, then that will make the problem go away. Again, it's sadly a little bit beyond the scope of the class to explain why that's the case, but the Cliff Notes version is that volatile guarantees atomic reads and writes. So if you make something volatile, then if you set M done to true and it's volatile, it'll go straight through to memory and not get stuck in a multi-core processor cache. And there's a whole slew of other atomic things. There's the volatile qualifier, which we see up there. There's also atomic objects like atomic Boolean, atomic integer, atomic lock, atomic reference. There's a bunch of other things that are atomic. So those are ways to solve that particular problem. The last piece of the puzzle for this discussion is how synchronizers themselves can cause concurrent programming hazards, which seems a little bit wacky, but it's true. So you might think you're protecting yourself from memory inconsistencies or race conditions by using synchronizers, which is good. But if you're not careful, you can actually enable other concurrency hazards, in particular deadlock. So what is deadlock? Deadlock occurs when two or more competing threads are waiting for the other threads to finish, and thus none ever do. And here's a really good example of how you get yourself into deadlock. This is a little example. This is the canonical example of deadlock. We have thread T1, which owns lock L1 and needs lock L2, and thread T2 owns lock L2 and needs lock L1. So this thread T2 is trying to get something that thread T1 has, and vice versa. And if they're not careful, they will end up in the deadly embrace. And so if you're in a deadly embrace, then everybody's waiting and nobody's making any progress. There's lots of famous examples of this from the theory of concurrency, things like the dining philosopher's problem and so on and so forth. And you may learn about that if you take a course in computation at some point. There's various ways to get yourself out of or to avoid deadlock. So here's another example. This is a simpler example that demonstrates deadlock just for kicks. Let's assume for sake of argument that thread T1 calls method M1 and thread T2 calls method M2 at the same time. What happens here is that we're going to synchronize, thread T1 is going to synchronize on the string class. Thread T2 is going to synchronize on the integer class. And then thread T1 is going to try to synchronize on the integer class, which is locked. And thread T2 is going to try to synchronize on the string class, which is locked. And so now we're in a classic deadlock situation. How do we solve this particular problem? It's quite simple for something like this. Always acquire your locks in the same order. So if we always acquire the integer lock followed by the string lock, then you'll avoid this particular type of deadlock. Now, that seems like an easy solution, and it is. But the problem is if you start building your code where these synchronizers are hidden behind abstraction barriers, like public and private in a class, it's not always entirely clear what locks are being acquired and in what order. So to really solve, or one way to solve the deadlock problem is to kind of expose something about your locking hierarchy. And there's a whole pile of cool concurrency stuff about detecting deadlock and avoiding deadlock. We are not going to talk about that. In fact, we're going to try to avoid deadlock in our course because we're going to try not to share anything. So that'll solve a lot of the problems. Here's another example if you want to actually try this stuff out. There's an example that's available on my website in my GitHub repository called Deadlock Queue. And it's kind of cool. It has two threads calling transfer, and one calls transfer with a source object and a destination object, and then transfer, the other thread calls transfer with destination and source reversed. So of course, once again, we're going to end up deadlocking under some circumstance. The thing that makes deadlocks so tricky in a concurrent program is depending on the order in which the threads run, they may or may not always deadlock. Because it might turn out that one thread comes in, acquires source, acquires destination, does its thing, no deadlock. It's only under certain circumstances where they both come in at the same time. One grabs source, the other grabs destination, and then you deadlock. That's what makes deadlock so pernicious. It doesn't always happen. So it's sometimes, and it's also one of those things where the very act of debugging your program may change the program's behavior. And that's what's called a Heisenbug. Those of you who are physicists will appreciate why it's called a Heisenbug. For those of you who are not physicists, it's called a Heisenbug because the Heisenberg uncertainty principle says the very act of looking at something can change its behavior. So there's a whole almost philosophy of physics about killing cats and things like that, who killed Schrodinger's cat, and so on. Not that I'm advocating killing cats, by the way. Okay, so that's the end of the discussion of Java concurrency hazards.